So if you didn't pick up your exam on Thursday, your graded exam is right here. I also updated the grades online. If you were in class on Thursday and picked up your exam, make sure to turn it in because I have to put in your grades. I didn't have access to your graded paper, so I couldn't update your grades. Okay. There's also a couple of people submitted their homework, submitted a soft copy of their homework. They are also there, the graded ones for homework 2. And there is also a print of text of the examples that we are going to solve in class here. So if you haven't picked up any, make sure you do so. And yeah, and I assume all of you received my email yesterday. What I'm going to do, because we didn't have everyone in class on Thursday, what I'm going to do is I'm going to, if you have already submitted your answers to exam problems, you will get up to 20 bonus points, 20 points on the exam. I will also consider replacing your final exam grade for your exam 1. I'm using your final exam grade for the portion of the final exam that is from chapters 1 to 3 for your exam 1 grade anyways, if you do better, right? If your grade over there is 100 and grade here is 56, your exam 1 grade will become 100, right? The same is going to be true for exam 2. So if you don't do well on the exam 2, but if you do well on the exam 2 section of the final exam, I will use that part of the grade for you. Does this make sense? Okay. So just in case you don't do well on any of the exams, you have the opportunity to make up for it. Okay? Is there any questions? No. Your homework 4 will be uploaded either Thursday. I have to go back to the syllabus and check out the date. But it will either be uploaded on Thursday or Tuesday, and it will be all of Chapter 5. Right? It will cover all of Chapter 5. Chapter 5, we started talking about Chapter 5, if you recall, in the previous lecture. The idea was we are going to use the Reynolds transport theorem, which was the topic, one of the topics of Chapter 4, to derive the main equations for fluid flow. I'm just going to rewrite the Reynolds transport theorem just in case. OB. Again, just to make sure we are all understanding what's going on here, the idea was changes of a B parameter, an extensive B parameter in a system over time is equals to changes of the intensive parameter, right? B equals to M multiplied by a small b, right? The intensive parameter inside the control volume plus the fluxes over the surfaces. To give you an example to better understand this, let's say you have this type of control system that is passing through this control volume. Changes of variable b inside this control system is going to be equal to changes of intensive variable b inside this bigger control volume plus whatever of that thing that is, whatever the fluxes on the boundaries. So whatever is going out or coming in into the control volume. Okay, that was the idea of the Reynolds transport theorem. We're going to use this idea, get this equation, and find the main equations that govern the fluid flow, the motion of the fluid, right? The first thing you want to find is the conservation of mass. Since we are dealing with conservation of mass, your extensive property, capital B, is going to be equal to your mass, right? Which means your intensive property is going to be equal to B divided by M, M divided by M. Your intensive property is going to be 1. Again, we want to apply this equation, the Reynolds transport theorem, to mass, right? We want to use the mass as an extensive property. So let's plug this in. Changes of mass of a system with respect to time has to be equal to the changes over time, the integral over the control volume of rho divided by 1 multiplied by the elements of that volume plus integral over the control surface. These are the surfaces of the control volume, rho multiplied by 1, which is your intensive property, multiplied by the okay. Before moving on, I just want to make sure we are clear on all of the parameters that are used in this equation, right? Again, this B of system is a property, an extensive property of the system. T, of course, is time, and this is capital B, capital D, which stands for total derivative of that extensive property with respect to time. We have learned about total derivatives in chapter 4. I can see some examples in your homework as well, taking the total or substantial derivative. This part, we are taking the derivative with respect to time over the control volume, right? So changes of that property inside that volume. And if this intensive property doesn't change inside your volume, so remain constant all over this control volume, we can take this out just to, and you just want to make sure that we are understanding what this equation represents. Okay, let's take that out, just this part. I'm assuming that this B doesn't change over the volume. So this essentially means that it is constant with respect to volume. We are going to treat it as a constant. You can take it out of the integral. We are going to treat it like a 2 or a 1 or whatever, right? Integral of control volume of rho dV, right? In most of our analysis, we assume density is also constant, right? Which essentially means that we are dealing with the integral of dV, right? Which is integral of dV is your total volume, right? So if these things don't change with volume, this is what we are going to get. V rho V. What is rho V? Is M, right? M equals to density multiplied by volume. If these don't change with inside your control volume, right? That's a huge if. So I'm just making these assumptions to make sure we understand what this equation represents. Okay, so M multiplied by your intensive property is going to be the extensive property. But this time for the control volume. So changes of the extensive property B or in the controls in the system is equal to the changes of that extensive property in your control volume plus whatever that has moved out of your system or moved in of your control volume or moved in the control volume. How can we understand this part? Is talking about the inlet and outlet out of the boundaries or inside the boundaries. Again, let's assume that rho and B doesn't change. over the areas. We are taking the integral this time over this control surfaces. So over the surface, not the integral, right? Integral of control surface, Vn dA. What is this V dot N? N always stands for the normal vector. Vector is normal, the unit normal actually. That is normal to your area, to your surface. Our surface here is dA, or the area, right? So we are talking about this unit vector. When you multiply your V, your velocity vector, by a unit normal, what you're going to get is the velocity component that is normal to the surface. Okay? So this is the only part, the velocity component that is normal to whatever outgoing or ingoing surfaces, right? So velocity component normal here changes direction. It has to be normal to that specific part of the surface. Does this make sense? So if your velocity is going out of the control volume in this direction, in this calculation, you only care about the normal component of it. Again, if we assume that velocity is also constant and doesn't change, we can take it out. Okay. And then we are taking the integral of dA over the surface area. So we are dealing with rho BVA area. Rho BA, or AV, rho VA actually, is m dot, right? Rho VA. This is something we have seen before, right? Okay. So we can replace it with m dot B. Or how much this extensive property changes goes out of the control surfaces. Okay. So changes of extensive property in a system is equals to changes of that extensive property inside the control volume, plus whatever that extensive property that is moving out of control volume or coming in the control volume. Okay. To better visualize it, your book actually has this example, and we talked about this. Let's say this is your general control system, your general system, right? Again, inside this control volume at time t equals to 0. Again, control volume at time t equals to d1. Your system has moved out of the control volume, right? So this will be whatever volume that has gone out. This will be this part of the system, right? And then the changes of this value property inside the control volume is going to be this minus the control volume, right? Whatever that has moved out. Okay, does this make sense? Hopefully. Okay. So just to make sure we can better understand what this Reynolds transport theorem stands for. Okay, so we have replaced, we have used M as the extensive property, which means that for your intensive property, you're going to have 1 because intensive property was defined as the extensive divided by the M. Okay. But what was the changes of mass of a system? We define a system as something as like a volume or a selection in a space that doesn't have any mass flow out or in, right? Which effectively means that mass of a system is constant. So for a system, changes of mass over time is 0 That's based on the definition of the system, right? This is how we define the system. So this part is going to be 0 based on definition. Okay? Then our equation is going to become this. Rho dV plus rho dN dA is equals to 0. What does this mean? What does this equation tell us? This tells us that the changes of mass inside a control volume is equal to the total mass in minus total mass out, right? If total mass in is equal to total mass out, then there is no change of mass inside the control volume. The mass is going to remain constant inside the control volume, right? If somehow you're creating mass inside the control volume, then m dot in is not going to be equal to m dot out. Okay? Any questions about the conservation of mass equation? Again, we usually express the mass flow rate as your flow rate multiplied by your density, or a flow rate is AV multiplied by rho. We usually say rho AV, but it is the same thing, right? That's for the case where your velocity is uniform in the outlet. So let's actually talk. Let's say you are dealing with a flow inside a pipe. Velocity is coming in with this distribution, which essentially is telling us the velocity of this flow does not change with respect to y. Velocity is always going to be equals to v infinity. It is possible for the velocity, actually in reality, that's what happens. Your velocity is a function of y. So this is going to be the distribution, the real distribution of the flow inside the pipe. Okay, which means that the velocity is a function of y. It's going to go from 0 to a maximum value to a 0, right? So if this is the case, then we can find the mass flow rates on a surface by just multiplying density by the area, that's the cross-sectional area of the pipe, multiplied by the density. But in our equation here, we are not making any assumptions about the velocity. So the mass flow rate over the mass flow rate of a surface is going to be equal to rho, the integral over the control surface, rho Vn dA. Again, this is a representation of the same integral if your velocity is distributed uniformly. If not, if your velocity is distributed like this, you have to take this integral, which is not that hard to take. We usually, I mean, it looks very frightening, I get it, but we usually assume rho is constant. So we usually take it out of the integral. And then as long as you know the distribution of velocity, let's say your distribution is y squared plus y, right? And let's say you are dealing with a two-dimensional case, which means that your depth of this pipe is a unit value, 1 meters. So your dA is a small element of area is going to be dy multiplied by this 1, right? dy. So this is the integral you have to take from 0 to whatever maximum y is, right? So when you put it, when you solve an example, it's going to become a little more clear. But let's just keep the integral as is at this point. Okay. What if we want to find the average velocity, right? Let's say your velocity distribution is non-uniform, right? How can we find the average velocity? That's actually by setting these two equal. By average velocity, we are mainly assuming that that average velocity is uniformly distributed, can replace your non-uniform distribution, right? That's the idea. Let's call that V bar. So the assumption here is that rho A V bar, or average velocity, has to be equal to the solution to this integral. Which means that your V bar is going to be the integral divided by rho A. So in a non-uniform velocity field like this, if you were to find the average velocity, this is the equation you want to use. Is there any questions? No. Okay. So let's solve the first example. That's example 5.1 on a printout, the handouts you received. If you are watching this online, you can go download the handouts from the Blackboard website in the contents tab in chapter 5 folder. Okay, so example 5.1 is telling us a great danger to workers in confined spaces involves the consumption of breathable air. Before reading this, one thing I'm probably going to do for your next exam is to remove all of these explanations, the unnecessary explanation that may become a source of confusion. So I'll probably give you a straight question, right? But we have it in the example, so we have to read through it. So a great danger to workers in confined spaces involves the consumption of breathable air and its replacement with other gases such as carbon dioxide. To prevent this from happening, confined spaces need to be ventilated. Although there is no standard for air exchange rates, a complete change of the air every 3 minutes has been accepted by the industry as providing effective ventilation. So one piece of information: complete change of air every 3 minutes. Okay. A worker is performing maintenance in a small rectangular tank with a height of 10 feet and a square base 6 feet by 6 feet. So we have a tank. $10 feet, 6 feet, 6 feet. And fresh air enters through an 8-inch diameter hose and exits through a 4-inch diameter port on the tank wall. So we have a hose, an 8-inch diameter. It doesn't really matter where they are, but we are going to assume that they are on the side walls. 8-inch diameter. Okay. The flow is assumed steady and incompressible. Steady, incompressible. Okay. So, and we are told to find the exchange rate needed for this tank based on this standard and the velocity of the air entering and exiting the tank at this exchange rate. Okay. So let's actually use the equation, the conservation of mass equation. This was the main conservation of mass equation. Okay, equals to 0. How can we simplify this based on whatever we are given in this problem? The first thing is we are told that this is a steady problem, right? A steady state problem. What does this mean? Constant with time. So this part goes to 0, right? The changes with respect to time in the equation will go to 0. That's it. Okay? So your equation will simplify to integral over the control surface, rho Vn dA equals to 0. But we are also told that the flow is incompressible, which means that density does not change with time or is constant, right? That's the idea. So we can take density out of this equation as well. Eventually, this is what we are going to get. Equals to 0. We can actually make one more assumption that is hidden in this question. The one more assumption we can make is that since these holes are much smaller than the tank, we can assume the velocity that is coming in and going out through these holes is actually distributed uniformly, because this whole dimension is much, much smaller than the tank, right? So this is the situation, right? So we can take this out of the integral as well. And we can also, the other assumption we are going to make, which is not just an assumption, it's actually true statement, that the velocity is going to be normal to the surface, right? Yes. What do you mean by that? They have different velocities, right? They are not the same velocity. They are just distributed uniform individually, right? So let's say this is the side view of your hole. One of the holes, velocity is distributed uniformly. And this is the smaller one. Again, a different velocity, but distributed uniformly. Okay. Or the other assumption, you didn't need to make the assumption. You just could have said that I'm calculating the average velocity, right? That would have worked as well because the holes are so small. Okay, so we can take and the idea was the velocity is also normal. So v dot n is equals to v integral of dA over the control surface. That's a double integral of dA, which means that we are dealing with A. Rho VA in minus rho VA out is going to be 0. That's the idea, right? We have two control surfaces here, one coming in, the other one going out. So we have two integrals. That's the end of the day, which simply means that m dot in is equals to m dot out. Okay. So this is the equation we need for this problem. We didn't need to derive the equation from this huge integral equation. We could have probably guessed this is the situation. M dot in is equal to M dot out, right? This is something you have seen before. But I just wanted to make sure that we can simplify the equation. First part, the exchange rate needed for this tank. So all of the volume of the tank has to be replaced every 3 minutes. The exchange rate is going to be volume divided by 3, right? It's simple. What is the volume of the tank? 6 by 6 by 10. So 360 cubic feet. And the exchange rate, Q, or volumetric flow rate, is going to be equal to total volume divided by the time the exchange, that complete change of air every 3 minutes, right? That's the time we need to change all of the air inside. So 360, 3 minutes, how many seconds that is? 180 seconds, right? So you can actually, your book has done it in cubic feet per minute, but I'm going to do it per second. It doesn't really matter. So we're going to get 2 cubic feet per second. Okay, is this clear? Part B. Part B is asking us to find the velocity of the air entering and exiting the tank at this exchange rate. So we are told this is compressible, right? So from this equation, these two parts will cancel out. And AV in is equals to AV out, right? And all of this is equals to Q, right? That we have already calculated in part A. 2 cubic feet per second. So let's say 2 is equals to, let's take the in part first, V in multiplied by the area in. That's an 8-inch diameter. Pi d squared divided by 4. You just have to make sure that you are converting inch to feet or the other way around. How can we convert inches to feet? How many inches are in a feet? Or, yeah, how many inches are in a feet? 12, yeah? 12. So this is V in multiply. Let's do the first one first. Pi 8 divided by 12 squared divided by 4. Can someone calculate this for me if you have a calculator? 8 divided by, actually we can calculate it, that's easy. V in pi 64 divided by 144 divided by 4. That's 16. What's equals to 2. And that's 8. So 144. So your V in is going to be 144 divided by 8 pi. That's in feet per second. And then you do the same operation for V out. The only difference is going to be the area, right? Area is the only thing that is different. Is this clear? Okay. So let's move on to the next example. Next example, that's example 5.2. It tells us air flows steadily between two sections in a long straight position of a portion of a 4-inch inside diameter pipe as indicated in the figure. Let me just draw the figure on the board and we'll go from there. Okay, so we have a control volume inside the pipe, 4-inch diameter pipe, right? The diameter of the pipe does not change. Is going to be equal to 4 inches, and the uniformly distributed temperature and pressure at each section are given. We have the pressure and temperature at that's 100 psi, and temperature is 540 degrees Rankine. P2, we are also given the pressure, 18.4 psia. T2 is 453 Rankine, and V2 is 1,000 feet per second. The average air velocity, so we are told that the velocity distribution is not uniform, but we are given the average air velocity at the outlet at part 2. Okay, we want to calculate the average air velocity at section 1. Okay, we can start with the main conservation of mass equation. Well, we don't need to because we are asked to find the average air velocity. All right. So m dot at 1 is going to remain constant. There is no generation. There is no injection of mass to the control volume here. So m dot 1 is equal to m dot 2. And since we are dealing with the average, we can go to the equation for the average mass flow rate directly. Okay. What can we say about the areas? They are the same. Yeah. So we can cancel them out. Right? Can we say the same thing about densities? No, we cannot say the same thing about densities. Why? Because we are not told that this is an incompressible case, and we are also given pressures and temperatures. This is one sign that your density is changing, and this density is the only thing that is changing, right? Which, if it wasn't changing, this whole solution would have been a moot point because the velocity wouldn't have changed, right? Okay. Well, how can we find the density at each cross section? Ideal gas law, that's it. What is ideal gas law? Is P divided by rho is equal to P divided by rho RT, P2 divided by RT2. We are given the pressure and temperature, and we only need to have R, which is usually given to us. But we don't need to have R here. And I'm going to tell you why. So let's say we have these equations, these two equations, the ideal gas law for density, and we have this. We are trying to find the average velocity at point A. So let's rearrange this equation. V1 is going to be equal to rho 2 divided by rho 1 V2, right? That's the idea. We are going to use these ideal gas law equations here. So rho 1 is P1 RT1 divided by P1 P2 RT2 by average velocity at point 2. Here r's are equal, they will cancel each other out. So you don't need to have the r here. You can just cancel it out. If you were told to calculate the density first, so if you needed a value for density, you needed to have r, but here we don't need a value for density. So you plug in pressure, temperature, and pressure and temperature and velocity again. You just have to make sure you are consistent in units, right? We are given pressure in PSIA. What is PSIA? Is it in inches or feet? Inches, right? But we are given the velocity in feet, right? Feet per second. So you just have to make sure you are consistent when it comes to units. But then again, since we are taking the ratio here, the units will cancel each other out. So just can plug it in, and it will give you the same result, right? So are we clear on how the units are going to be consistent? Do we need to convert them or not here, or no? No? Yes? OK. So I'm going to take it as a yes. And then you plug in the numbers. Your V1 is going to be 219. That's the average velocity at 1. 219 feet per second. OK. Next example. Example 5.3. The inner workings of a dehumidifier are shown in this figure. Moist air, which is a mixture of the dry air and water vapor, enters the dehumidifier at the rate of 600 pound mass per hour. Let me. So the moist air comes in to the dehumidifier at the rate of 600. I'm going to say m dot of moist air. 600 pound mass per hour. Okay, liquid water drains out of the dehumidifier at the rate of 3 pounds mass per hour. So m dot of liquid water, 3 pounds mass per hour. We have a simplified sketch of the whole process that is given to you. We have m dot 1, which is your 600 pounds mass per hour. We have liquid water drainage, and this is your liquid water with m. We're going to call m dot 3. So this is m dot 1, m dot 2, m dot 3. I'm sorry, m dot 3. M dot 2 is the air is going out. There is also a fan here. Okay. And we have a cooling coil. M dot 4, M dot 5. Okay, we want to determine the mass flow rate of the dry air and the water vapor leaving the humidifier. How should we determine that? So we have mass m dot 1 coming in, which is the moist air. We have liquid water going out, and M2 is a combination of dryer and some liquid water, right? M4 and M5 are the coolant, a mass in and mass out. How can we calculate M2? M2 is a parameter of interest here. Think about it. This looks like a very complex problem. This may look like a very complex problem, but in fact, it's one of the easiest problems you can deal with. Okay. And the idea is mass is conserved, right? So whatever is coming in has to go out. What is coming in here? We have m.1 coming in and m.4, right? What is going out? m.5, m.2, and m.3, right? So a combination of the two sides, I mean, the addition of the in parts has to be equal to the addition of the summation of the out parts, right? But, and that's a huge but, the coolant here does not mix with the air, with the moist air and water. So the coolant part does not come into the analysis of air, right? The coolant is a separate control volume. So those are just trig values. You don't need to use them, right? Because it's just the coolant, right? It does not mix with your air. So there is no mass transfer between the coolant and the air and water, okay? So it becomes even simpler. M.1 is the mass in is equals to mass out, which is m.2 plus m.3, right? M.1 is given to us 600 pounds mass per hour. M.3 is 3 pounds mass per hour, which means that M.2 is going to be 597 pounds mass per hour. Okay. Next example. This next example is actually a little more complicated because it involves actually taking the integral. So just don't freak out. Don't freak out when you see something like this. Try to simplify the problem as much as you can, and I'm pretty sure you can figure it out. We are given an incompressible laminar water flow that develops in a straight pipe having radius r as indicated in the figure. And this is the figure. Okay. We have this water pipe. The control volume inside it. Okay. And we have the radius of the pipe is capital R. The velocity profile is uniform at section 1. What does a uniform velocity profile mean? This means that it is not a function of R or Y or anything, just a constant value at any point of that cross-section 1. Okay? That's a uniform velocity profile. And parallel to the point axis everywhere. At section 2, the velocity profile is axisymmetric and parabolic. Let me actually use a different color, or we can just remove these parts of the pipe. So parabolic and axisymmetric. Okay. And with zero velocity at the pipe wall, so velocity 0 here, the pipe wall, and the maximum velocity at the, it's called the Umax, at the center of the circle, at the center line. Okay. We are also given the formula for distribution of velocity. Velocity at point 2 is equals to your maximum velocity 1 minus r divided by r squared. A small r here is the distance from the center line. So a small r changes from 0 to r. Okay. We want to find the relationship between this uniform velocity, capital U, and the maximum velocity. What is the relationship between the two? That's part A. Part B, and we're going to talk about part B later. So do we understand what the problem is? We have flow inside the pipe, right? Flow comes in with a uniform distribution at one side and is going out with a non-uniform distribution on another side, right? And we have the equation of that non-uniform distribution. And we are asked to find the relationship between this uniform velocity and the maximum velocity of the non-uniform part of the flow. How can we find that? How can we find this relationship? Do we have any guesses?
So would Umax be equal to U for this case?
No.
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 I'm just trying to think, like, when that was the average velocity we did last time we had parabolic. That was.
Well, what is the equation that applies here? The main overarching equation. Some mass is coming in, some mass is going out.
It should be density times area times velocity.
That has to be constant, right? Your m dot actually has to be constant, right? Or conservation of mass. That's the equation we have been talking about. So we are going to use conservation of mass to find out the relationship between the two. Since we have uniform velocity on one side, this essentially means that m dot of 1 is equal to m dot of 2, right? We don't need to go back to that long equation to get to this point. But m dot 1 here is going to be rho a1 v1, right? It's a uniform velocity distribution. But on the other side, we don't have a uniform distribution for m2. And we cannot use the average value because we want to have U max present in the relationship. So what should we do? We have to take, pardon me? Yeah, I was asking. Yeah, go ahead. Replace what with U max? This equation? Okay. That is you are moving in the correct direction, right? But the problem here is the velocity is not uniform, right? So if you recall, in the main conservation of mass equation, we had partial t, contour volume, rho dv, right? Plus cs rho dA, right? This part is 0, a steady state conditions. So which essentially means that whatever coming in is going out, right? For the part coming in, this velocity does not change with a, so we can take it out of the integral, right? So eventually it will become rho a1 v1. But for the outgoing part, this velocity changes with location. So changes with y or a for that matter, right? So we cannot take it out of the integral, right? But we have the distribution with respect to r, okay? And we already know that the velocity is always normal to this surface area, right? This is the surface area we are looking at. The cross-section velocity, based on what we see here, is always normal. So this part of the equation is going to be the integral over the control surface. Rho is constant. We can take it out, incompressible. V dA. And we also have the distribution of V, right? Or U2. Doesn't really matter. The same thing. Okay. So let's plug that in. U max 1 minus R dA. Can we take this integral as is?
DA actually is fine elsewhere. In the problem, it states DA2 is equal to the circumference times the radius. So we can replace DA in this case with that.
2 pi R dr, right? Not R. Not the radius dr. Yeah.
Like DA2 equals 2 pi r times dr.
Exactly. So that's where I wanted to get. That's what I wanted to get at, right? Here, our variable is R, right? A small r. R changes from 0 to R, right? But here we have dA. We cannot take the integral of a variable with respect to something else, right? Unless we know the relationship between the two, right? But dA here is a small element of area on the surface, right? Area of a circle is pi r squared. dA is a derivative of this, which is going to be 2 pi r dr, right? Does this make sense? Okay, so, and this was actually given to you in the text of the problem as well. So 2 pi r dr. So at this point, we should be able to take this integral because U max is constant. You can take it out of the integral. Just the maximum value of velocity doesn't really change. This capital R is the radius of the pipe. That doesn't change as well. 2 pi, also a constant. You can take it out as well. And the only variable is R, which we want to take the integral of which. We want to take the integral of which with respect to itself, R. So let me take the constant out as much as possible. Rho U max 2 pi integral of 1 minus r squared, r divided by r squared, multiplied by r, there's an r here, dr. And we already know that this small r changes from 0 to capital R, right? The radius of the pipe. Okay. Let's multiply this, whatever inside this parenthesis, by this r here. So we're going to get r cubed to r squared. What is the integral of this? The integral of r dr is r squared divided by 2, right? Integral of r cubed by this r squared, this is a constant value, like 2, 3, 4, whatever, is going to be r to the 4 divided by 4. Is this clear? Okay. So I'm just going to continue here. So the solution to this integral is going to be rho, or let's actually start with 2 pi rho u max r squared divided by 2 minus r to the 4 divided by 4r squared from 0 to r. So if you use 0, you're going to get 0 here. But if you put in r, you're going to get r, the capital R squared minus 2 minus r to the 4 divided by 4r squared. Let me actually put that in here. Minus 0, whatever. So this part will be the solution to your integral. R squared, r to the 4. This will cancel out. So we're going to get r squared to the 4. And this is essentially 4r squared divided by 4 minus, I assume you know how to do this simplification here. So I'm just going to replace it with the final answer. Are we clear on what happened here? Taking the integral, all of this. The other side is rho a1. A1 here is pi r squared, right? So I'm going to continue on the other side of the board. So, and we can actually cancel out the rows because rows doesn't change. So I'm just going to write this simplified version, pi r squared. What is V1? V1 is U, capital U, equals to 2 pi. We have already canceled the row out. U max, 3r squared divided by 4, right? R squared will cancel out. Pi will cancel out. 2 here will go with 4. We're going to get 2. So U max is going to be 2 by 3 U. Or there shouldn't be any 3's here. I made a mistake somewhere, but I don't know. But eventually, this is what you're going to get. You're going to get U max is equals to 2U. Let me see where I made the mistake. This solution to integral is r squared divided by 4. That's right. That's where I was wrong. Okay. So we have the relationship between U max and the U. U, capital U, is the velocity, uniform velocity at section 1. And U max is the maximum velocity on the cross section 2. Okay. Next part of the problem is asking us how are the average velocity at section 2 is related to U max. What is the relationship? So we need to calculate the average velocity at section 2 here. What was the equation for average velocity at section 2? It was the integral of rho Vn dA over section 2, which we have already calculated. This is the value of that integral, divided by rho A, or A2, right? So plug that in. You're going to get 2 pi rho U max r squared divided by 4. And here you're going to get rho pi r squared, right? cancel out, which means that Umax is equals to 2 multiplied by the average velocity. The conclusion you can make from this is that your uniform velocity is actually equal to the average velocity, right, at section 2. And the conclusion you can make from this conclusion is actually the fact that an average velocity is a good substitution for a non-uniform velocity distribution, right? Because think about it this way: is the average velocity is equals to the velocity here. This essentially means that your mass is conserved. Like rho AV or rho AU is equals to rho AV average 2, right? So we can substitute a non-uniform velocity distribution with its own average velocity in our calculation, right? Does this make sense? Okay. Let's move on to moving frames. There's another example on this topic that we are going to solve. I want to give you as a quiz, but you can actually do it later. Let's move on to a moving frame or a moving control volume. We talked a little bit about the moving control volume in the previous lecture, or I think 2 weeks ago on Tuesday, I think, yeah, so a week ago. And the idea was the fluid velocity is going to be equal to the velocity of the fluid relative to a non-moving frame minus the velocity of your control volume. So if your control volume, let's say this is your control volume, is moving at a speed vcv, and then you have fluid coming in and going out at velocity v, the total fluid speed is going to be v minus velocity of the control volume. You have to subtract the velocities. And in the equation for conservation of mass, for velocity, you have to use W, which essentially changes the Reynolds transfer theorem as well. This was the main equation for the Reynolds transfer theorem, right? Here, instead of V, we are going to get W. That's the only difference. So you just have to subtract the velocity you are given from the moving velocity, the control volume velocity, to get to the solution. Since this means that your conservation of mass equation is going to be equal to partial T control volume of rho dV plus integral over control surface of rho B W, no, there is no B, rho W and dA equals to 0. So this will be the equation for a non-deforming moving control volume. So all of the control volume is moving at the same speed, right? It is a non-deforming control volume. Because if it was a deforming control volume, then it would have been much more complicated. Very, very much more complicated. So let's solve another example with the moving frame, moving control volume. This is example 5.6. So we are jumping one example. An airplane moves forward at a speed of 971 kilometers per hour. Okay. So the velocity of the plane is 975 kilometers per hour. Okay. As shown in the figure, the frontal intake area of the jet engine is 0.8 meters squared. Let's actually have the jet engine. Let's say this is your jet engine. Very bad depiction, but A1 is 0.8 meters squared. And the entering air density is 0.736 kilograms per cubic meters. A stationary observer determines that relative to the Earth, the jet engine exhaust gases move away from the engine with a speed of 1,050 kilometers per hour. So V2 here, 1,050 kilometers per hour. That's the exhaust gas. And the exhaust gas density, ρ2, is 0.515 kilograms per cubic meters. Also, we are given the exhaust area. That's 0.558 meters squared. We also have the mass flow rate of the fuel. Let's call this m dot f. You're adding fuel to the jet, of course. We want to estimate the mass flow rate of fuel into the engine in kilograms per hour. Okay, let's see. What else do we have? So we need to find the W's for each of these things. That's the first thing you want to do. What is W1 here? The speed of the plane. So 971 kilometers per hour. What is W2? That's the speed of plane plus V2. Why is that a plus? Because they are moving in opposite directions, right? So negative and minus is going to be plus. So 1,050 plus 971 kilometers per hour. Okay. And let's go to the main equation here. It is a steady problem, a steady state problem. So changes with respect to time are 0. Okay. And we are going to get integral of CS Wn dA is equals to 0. We are not given any information about whether the incoming or outgoing flow is distributed uniformly or not. So we are going to assume that the flow is distributed uniformly and make all of the assumptions we could have made here, right? Which this essentially means that m dot in is equals to m dot out. Pretty simple, plain and simple, right? And all of the m dots, we are making the assumption that the velocity is distributed uniformly everywhere, right? So all of the m dots are going to be equal to rho AV, right? Or we are using average velocities, rho AV average, right? So we don't have to make take any of the integrals. Does this make sense? Velocity distributed uniformly. Velocity uniform. Which means that we can take this velocity out, we can take the density out. Integral of dA is going to be A. M dot is going to be equal to rho AV. And this m dot in, what are the m dot ins? Is m dot f plus m dot 1, right? So And that has to be equal to m dot 2. What is m dot 1? Is rho 1, A1, B1, or W1. In this case, we have a moving frame, plus m dot f is equals to rho 2, A2, W2. Okay? And we have all of the parameters we need. We have rho 2, we have A1, we have rho 2, rho 1, we have A1, A2, we have W1 and W2. So we plug the numbers in, and you get m dot f to be 9,050 kilograms per hour. Do we have any questions? Okay. I guess that's it for today's class. In the next class, we are going to talk about deforming control volumes, right? Right now, we are talking about moving and non-deforming control volumes, but we are going to talk about deforming control volumes in the next class, and the momentum equation. And also, we will have a short discussion on energy equation. Hopefully, we'll be done by this chapter. We'll finish this chapter by Thursday and move on to chapter 7 on Tuesday.